Hello everyone, thanks for joining in. Today I'm going to present to you SEVurity, which I wrote together with Jan Wichelmann, Matthias Morbitzer and Thomas Eisenbart. Now, SEVurity is about AMD's memory encryption technology SEV, which aims to protect a virtual machine from a malicious hypervisor. So, let's take a look at the standard VM setup here. On the bottom side here we have the physical hardware, on which the host OS and the hypervisor is running. In our case that's KVM. And on top of that, we have the virtual machine here with its own guest OS and its own user and application. Now, one of the main goals of virtualization is to isolate the hypervisor here from the virtual machine. And in order to achieve this, the hypervisor mediates all of the resource accesses of the virtual machine, so that it only accesses resources that it's allowed to. And yeah, this is good for achieving the isolation, but it has the downside that we now have to trust the hypervisor here, that it does not spy on the data or even manipulates it. And yeah, this may be fine if we are hosting on our own physical hardware, but not if we are hosting in the internet, so not if we are hosting the virtual machine from Amazon, for example. And now to combat this, we might think, okay, I just encrypt all of my data, then the hypervisor cannot learn anything here, right? Yeah, let's take a look at this approach. Now for the network traffic, this is fairly easy. Most network protocols are encrypted anyways, and since this data most probably goes over the internet, it also should be encrypted in the standard case. And here for the disk setup, there are also solutions available. We can use full disk encryption under Linux, so everything is encrypted here. But for the RAM here, the situation is a little bit more difficult because we cannot solve this problem here completely in software since we have a bootstrapping problem. How would we protect our software that encrypts the data from being manipulated, because the software itself is in the RAM as well. And yeah, we cannot really solve this without some kind of hardware support. And this is really critical because now let's take a moment and think about where the keys that we used here and here to encrypt the data are stored when they're in use. They are stored inside the RAM. So the hypervisor can just read them out and decrypt all of our data here and here. So the encryption we added is completely worthless against a malicious hypervisor as an attacker. And this is exactly where SEV steps in. It allows us to completely encrypt the RAM of the virtual machine with a key that is not accessible by the hypervisor. And it achieves this by some hardware modification, as indicated by this trust bubble down here. Now, let's take a closer look. Here we have the CPU core and the RAM. And in order to achieve its security goals, SEV uses the secure processor of the Zen platform. And this has some kind of management functionality. It offers an API to the CPU core, and there it can request the creation of a new key, which the secure processor then creates and stores in its protected memory so that the hypervisor cannot access it. And then it also programs the key here into the memory controller. Now, if we make a memory access then, we use the ACID that comes along with the memory access. That's short for address space identifier. And we use this value to index, to get the correct key, to index this key array here. And then the data goes through the encryption module here. And in addition, we can control whether the data should get encrypted or not on a page-wise level. And for this, we can use a specific bit in the address that we use to access the data. And if this bit here is set, then the data gets encrypted and otherwise not. And there's no kind of synchronization mechanism here. So we can write encrypted data at one point in time, then we unset this bit and can read out the ciphertext. Now, in addition to these basic encryption features, SEV also allows remote attestation. This way, the owner of a VM can make sure that SEV is actually enabled on the machine, and also that the initial boot code that's used for starting up his VM is correct, and that the hypervisor did not place any backdoors or any malicious code there. And lastly, the secure processor here also allows the VM owner to build a secure channel into his VM, and this can be used to provide secrets into the VM. And yeah, this is really critical because it allows the VM owner to simply send over a completely encrypted disk image to the hypervisor. And then with the secure channel, he can provide the disk encryption key after he verified that the boot code is correct. Now, in the rest of this talk, we will analyze the encryption mode. And here we discovered a new updated encryption mode that actually paves the way for a more secure version of SEV. And in addition, we will look at the injection attack that we built in SEVurity. And this allows us to build an encryption oracle with really low assumption in comparison to prior work. And this encryption oracle also works with SEVES, which is the most recent available version of SEV, and it also encrypts some state variables, but as we don't need them for our attack, I won't cover this further. Okay, so what do I mean by low assumptions? Well, prior attacks on SEVES used self-generated network packages here to sneak data inside the VM. And then in order to operate stealthily, they also required a specific network service running here. And yeah, this makes them vulnerable to detection. Now, our construction, on the other hand, does not rely on self-generated network packages here. In fact, we don't need any control over the I/O operations performed by the VM at all. And in addition, we also don't require any service running inside the VM here. So this makes our attack applicable in a much broader scenario and also much harder to detect. Okay, let's move on to the encryption mode, which is the kind of the cornerstone for our attack and also very important for the other encryption oracle attacks. Now the encryption mode on the left-hand side here, that's the one that was previously discovered by Du et al. And the mode on the right-hand side here is the one we discovered in SEVurity. And as you can see, the only difference is that there's an additional XOR here on the bottom. Now, the advantage of this is that it protects the tweak values or the tweak function here much better than this version. So with this updated mode, it's much harder to get tweak values. And as you will see, knowing the tweak values is really important for our attack as well as for the prior attacks. Now these tweak values here are static and shared across all VMs. And this means that these modes don't offer any integrity protection or freshness. However, the tweak function here did not change between the two modes on the CPUs that we examined. Now let's take a closer look at the tweak function here. It's actually very simple. For each physical address bit, there's a 16-byte constant here, but this constant is actually 4-byte periodic, so we only have 4 bytes of entropy here at most. And now if we want to calculate the tweak for a physical address that we access, then we simply look which bits are set here. So in this case, it's this one, and here this bit and this bit is set. And then we simply XOR together the tweak constants to get the tweak value for this access. Okay, now that the encryption mode is clear, let's take a look at the injection attack. And yeah, here we have a schematic overview of a memory access of the VM. Here we have the RAM that now contains the ciphertexts. And here we have the data that is read by the VM if it accesses the ciphertexts. Now our goal here now is to manipulate the data that the VM reads here as a malicious hypervisor. And the basic idea is that we exploit that we can still read and write these ciphertexts here. And this now allows us to build a database of ciphertexts with known plaintexts. And if this database is large enough, then we will always find an entry that we can copy over to the location where we want to inject a value, so it decrypts to this value there. Now let's take a look at this approach. Here we copied over this ciphertext here to this new location because we want that this address decrypts to B now. And there's a problem here because now the tweak values down here don't cancel each other out anymore because the ciphertext here was created at this address. So the tweak here is different than the one used for this address. However, since we know these tweak values, we can simply calculate the change that is made to be here and include this into a search when we're looking for a ciphertext block to copy over from a database. And this way we can break this countermeasure. Now, the graphic shown here only shows the XOR encrypt mode. However, the same attack is also possible with the XOR encrypt XOR mode. And here we simply need to XOR this tweak difference here to the ciphertext before decrypting it. Because otherwise, the ciphertext would be manipulated before it gets decrypted, and then we could no longer predict the value that is right here. Okay, now of course the relationship between the amount of data that we control per ciphertext block this way and the size of our database are exponential. So in a realistic scenario, we were only able to control the first 2 bytes, and for this we used the Linux kernel running inside the VM as a source of known plaintext ciphertext pairs. And the upper bound of control that we can get by copying around the ciphertext block is 4 byte because the tweak values are 4 byte periodic. Now 2 bytes of control out of 16 bytes, that doesn't really sound like much, But yeah, there's already a lot that we can do with that. So let's take a look at this code statement here, which could be part of some kind of login process inside the VM. We check if the password is correct. If not, we abort, otherwise we move on. And on an assembly level, this looks something like this. This test instruction here is roughly equal to this comparison. And then if the passwords here are not correct, we don't take this conditional jump here, but instead execute the code in the middle here, and this eventually leads to the call to this abort function. Now, if the passwords are correct, however, then we don't take this conditional jump here. Sorry, then we take this conditional jump here, and we move on to here, and execute the code that should only be available to authenticated users. Now, with our attack, we can simply swap out this block here with a block that starts with EB13, and that's an unconditional jump. So this jump is always taken, regardless of the result of this test instruction here. And this means, regardless of the password that we supply, we will always jump here and execute this code that should only be available to authenticated users. Now, a similar approach can also be done with the return instruction to shut down function calls. And for this, we simply inject these return instructions early on in the function. And the beauty about these methods is that we don't have to care about the uncontrolled 14 bytes here, because we simply jump over them in both cases here. And yeah, building on this idea of jumping over the uncontrolled areas, we can inject even more complex programs into the VM by using this pattern here. We simply inject 2 bytes of payloads, so 2 bytes that actually contribute to the program that we want to execute at the end of a block here. So the first 14 bytes are uncontrolled, and then we inject at the next block a jump instruction at the first 2 bytes, so the last 14 bytes here are uncontrolled. And this way we always jump over these uncontrolled areas and execute our program. However, there are limitations to this approach, and that is because x86 features many instructions that are actually longer than 2 bytes. And in addition, we're having a really hard time accessing a specific memory address because memory addresses are simply too long. We cannot inject them into a program. And yeah, to work around this, we came up with the idea of, okay, let's just inject a simple program into the VM. And by simple, I mean that the program only consists of instructions that have most 2 bytes, so that we can actually inject. And now we let this program calculate this more complex value that we want to inject. And yeah, there are 2 steps required for that. The first one is getting the data into a register. So we have to calculate it somehow. And while there are more clever strategies, obviously, let's stick with this idea here. We simply increment the register until we reach a certain value that we want to inject. However, we clearly cannot do this comparison here inside our program, because for this we would have to inject this value here. And if we could do that, then we didn't need this whole approach here after all. So the idea is, let's move this comparison step to the hypervisor. And for this, we emit a signal of sort every time we increment the Rex register here. So this could, for example, be a call to SEVurity, which is an emulated instruction. So it triggers some handler function in the hypervisor. Or we could place this code in a way that we can force a page fault every time Rux was incremented. Now the hypervisor simply has to listen to these signals and can deduce the state of Rux here. And if we reach the correct value, the hypervisor simply rewrites this code here to move on with the second step. Now, as I already said, we cannot write to a specific memory address because it's too long, but we can use the stack memory of the program, because this we can manipulate with short 1-byte instructions. Now, this has the downside that we first have to locate the stack memory inside the VM, and we have to make sure that it's actually correctly aligned, so that we are starting to write to a 16-byte block and not in the middle of it. But as you can read in the paper, this can be done now. And this means if we simply execute this here 2 times, then we have written 16 bytes and have created a full 16-byte encryption oracle. And the data that we injected here can now be used as code again. So we can move it to a different location and execute it as code there. And since we know the location of the guest kernel inside the VM, we can move our code inside the kernel and execute it with kernel writes inside the virtual machine. And this gives us full control over the VM. Now let's look at some countermeasures here. The first one would be to use the XOR encrypt XOR mode together with a tweak function that has higher entropy. Because as said earlier, it's really hard to get the tweak values with this mode. You basically have to brute force them. And if they have high enough entropy, that's no longer possible. And without knowing the tweak values, we can no longer predict how a ciphertext block changes when we copy it to a different location. And the other constructions for encryption oracles also have this problem. And this actually seems to be the case for the Zen 2 platform. We did some tests there, and it doesn't seem like the tweak values are 4-byte periodic anymore. However, the much stronger countermeasure would be to use cryptographic integrity protection that could actually detect if a block is decrypted at a different location or manipulated, because this would completely shut down the whole attack vector. However, it doesn't seem like AMD is planning to do that. Instead, in their future extension SEV, Secure Nested Paging, they will add a mechanism that will prohibit the hypervisor from writing to VM memory instead. Now, of course, this will also shut down our attack because we can no longer copy around these blocks, but we think that cryptographic integrity protection would be the much stronger choice. Now, let's conclude the talk with a quick recap. We have seen an analysis of the encryption mode. We've seen that it uses AES with static low entropy tweak values, has no integrity protection or freshness, and we also discovered this new XOR encrypt XOR mode that, together with stronger tweaks, could make the encryption mode more secure. And the second thing we've seen was the injection attack that allowed us to build an encryption oracle that actually works with SEVES, so the most recent available version of SEV. And for this, we used the guest kernel as a source to get non-plaintext ciphertext pairs, which we put in a database and used to get control of two plaintext bytes of a 16-byte ciphertext block. And building on this, we get control over a full 16-byte block by injecting this program into the VM. And this then eventually allows us to execute arbitrary code. Okay, that's it from my side. Thank you very much. I'm happy to answer your questions now. If you want to know more, you can also take a look into the paper or into our proof of concept code that's available on GitHub now.